molto grazie per l'introduzione. Mi scusa, però non parlo italiano, so I will do actually this presentation in English. It will be much better for me. So we'll talk actually about the selection and hybridization of yeast strains to modulate key compounds in wines. I will first talk about the impact of yeast on wine aromatic profile with a focus. I didn't know that actually Professor Gambuti was talking about that just before me, but a little bit of focus on acetaldehyde and sulfites, and then focus on acetate esters, and then a very, very simplified sum up. I will then talk about the yeast hybridization to overproduce esters and minimize sulfites. And then I will let the floor actually to Yorgos for the impact of the Saccharomyces pastorianus on Sauvignon Blanc, so a new species. And then we will have a final conclusions. As an introduction, I wanted to say that actually wine quality improved drastically over the last 30 years, and that's more and more exigence actually for the winemakers because high quality wines are now found everywhere. So the key actually for every winemaker now is to really make the difference with the other, let's say, wineries. And this differentiation is key, and differentiation is with the customer trends actually always through cleaner, so less allergenic, less alcoholic, so safer, let's say, and cleaner wines and more aromatic profiles towards mainly the fruitiness profile that is the customer's strength. And what is interesting in that trend is actually that one of the most important differentiation factor, at least for the fermentation, is actually the yeast and the selection of the yeast you do. So the idea is that this yeast can come from two really origins. That could be a selection from nature, from vineyards, isolated on berries, isolated on leaves, on soils, or in wineries, actually, and then different genus and different species. Could be Saccharomyces cerevisiae, we know the variety cerevisiae, variety Banus, Saccharomyces pastorianus, other species we saw during all the conferences. But then we can also generate these yeast strains, for sure, from the selection in nature first, but then from genetic techniques. And this can be done by mutagenesis of an existing strain, a directed evolution. You could even do GMO, actually, that is not for timing on the wine completely accepted, but in other segments, yes. And hybridization, that is actually another techniques to modify. So in one hand, you have the selection from nature, and you have natural specificity constraints, even if you select well your yeast. In the other side, you have this natural specificity that you want to improve in a targeted way. So it's quite complex to combine both, so to combine always great aromatic contribution and also great fermentation abilities. And that's the idea behind the selection of the yeast and this work. So a bit on the introduction first, on the yeast impact on wine aromatic profile, because we will mainly focus on that. Actually, what is yeast? Yeast is basically the microorganism that will do actually the fermentation and that produce the alcohol through the glycolysis pathway. But even through this glycolysis pathway, you have certain compounds that are released actually already. And these compounds can be acetic acid, that's not the nicest one, acetaldehyde, so we talked about that with Professor Gambuti just before, and some glycerol. But this actually pathway is going to a key compound that is the acetyl-CoA, and that's one of the base of most of the aromatic compounds. This acetyl-CoA is involved in the fatty acid pathway to produce fatty acids. If they are released out of the cells, that can have some cheesy notes, not really particularly interesting. Then from the yeast is able to use nitrogen source, amino acids or ammonium that interconvert into the cell, and then through the Ehrlich pathway actually are producing higher alcohols that are also the base of a lot of different aromatic compounds. Then the ability of the yeast to actually assimilate sulfate and to assimilate sulfite and to produce as well sulfites. It's interesting because it will be also involved a lot in the aromatic compounds, and we saw that with Marco Licalzi just before. From these sulfites, these sulfites can actually lead to the production of sulfur amino acids like cysteine, methionine. Cysteine is involved in the creation and the generation of glutathione, that is the most antioxidant compound in the yeast. That could be interesting, but could also lead to methionine, and if the methionine is going to the Ehrlich pathway, can lead to the methanol. So that's not really nice flavors. Anyway, actually from the acetyl-CoA and the higher alcohols, the yeast is able to produce acetate esters that have a strong, powerful impact on the aromas. And these actually esters can be so also from different amino acids, like phenylalanine will produce 2-phenylethyl acetate. From leucine will produce isoamine acetate that are key compounds. Other actually acetate ester is with the ethanol, and acetyl-CoA is ethyl acetate. And then you have all the other esters that we are called ethyl esters that are coming more from the fatty acid pathway and that are globally corresponding to the fruitiness. And you have the linear chain ethyl esters and also the branch chain ethyl esters that are actually done after the fermentation because the branched fatty acid needs to be released into the medium and then esterified with the ethanol. These all are fermentative aromas. And so all these compounds are impacted potentially by the yeast in different ways. But then you also have the varietal aromas, and the yeast has something to do with it. For the thiol precursors, taking the thiol precursors, internalizing these thiol precursors, and releasing free thiols like 4-MMP, 3-MH with these grapefruit aromas. Also a conversion because 3-MH is a 3-mercaptohexanol, so it's a higher alcohol that can combine with the acetyl-CoA to produce the 3-MH acetate. And this 3-MH acetate, as we saw this morning and yesterday as well, is responsible for all the passion fruit aromas. You have about the same things for the terpenes or the C13 isoprenoids. The only difference is that actually the enzymes are not inside the cell, they are mostly outside the cell. So that the yeast has a very strong impact on the aromatic profile. And if we want to focus a little bit more on acetaldehyde and sulfites, as we did just before, we see that acetaldehyde is the most important wine carbonyl compound. It's a key compound. Why? Because it's a terminal acceptor of electrons towards actually the alcoholic fermentation, so to produce the ethanol. So it's a key compound and it's strain dependent. Its production is strain dependent. It can be produced by the yeast, also actually generated afterwards from oxidation mechanism and oxidation from the ethanol, and then can be reduced by yeast and bacteria. And this acetaldehyde is actually quite closely linked to acetic acid and acetyl-CoA production, depending on the genes involved. This is to put in correlation also with sulfites, because we saw that actually, yes, yeast are able to produce sulfites. This is antiseptic, antioxidant, but their main problem is they are allergenic. And actually, they can be generated and or assimilated, but anyway, it's actively regulated. So all yeast strains doesn't have the same actually propension to produce the sulfites and the sulfites. So it's strain dependent, but one thing that is really important is that it's closely related also to the acetaldehyde because it's actually the acetaldehyde is the most important sulfite binding compound. And so there is quite a close relationship that we will see afterwards. Is there really an acetaldehyde and SO2 correlation in vinification? So actually it seems to exist because if the acetaldehyde is actually consumed, there is other production of sulfites to compensate or the other way around. So this is an experimentation and it seems to be quite correlated, but actually it's much more complicated than that. So in exactly the same conditions and depending on the conditions, the must, the other parameters that you see that this correlation, yes, there is a trend that yeast producing more total SO2 are also producing more acetaldehyde, but it's not completely true. Then we focus on acetate esters, and on acetate esters, actually what we see is it's coming from actually the condensation of acetyl-CoA and higher alcohols. So that's really interesting, esters, and they are coming from both pathways. So main pathways, the Ehrlich pathway and the nitrogen pathway, but they can come also from the glycolysis pathway. These are the main esters produced and responsible for a lot of fruity and floral notes, and like the isoamyl acetate, are major flavor enhancers even at low concentration. But they are really highly regulated. So you have a lot of genes involved, and especially the ATF1 and so acetyltransferase 1 and 2 that are involved in the production of these acetate esters, and that can be regulated a lot. So there are a lot of interconnections, and really simplified sum up could be that actually. The SO2 production seems to be related to the acetaldehyde production. The SO2 production, if it's released by the yeast or assimilate and released by the yeast as a resistance, most of the time, the most they are producing the sulfites, the most resistant they are towards sulfites. And then this production of acetaldehyde is closely related to the production of acetic acid and acetate esters as a subsequent. But this is really simplified, and it's much more complicated because you have a lot of genes involved that are actively overexpressed, underexpressed, or others, depending on the types of strains. So the idea of this was to actually start with hybridization to overproduce esters and minimize sulfites. So the idea was to get a clean and very fruity yeast strains by hybridization. And the challenge was always, when you do an hybridization, is to combine both parents' interests and to try to overperform their characteristics. So the parent selections were here. Actually, you have the parent one, for example, not a lot of interest, actually. It seems that there is not a lot of interest of this yeast in terms of vinification, but there is something very interesting. It was a very low producer of sulfite. And the other strain actually was much stronger, much more resistant, but actually with some problematic things like acetaldehyde production and SO2 production. So we wanted to hybridize these both strains. And to hybridize these both strains, we have to know if they are sporulating or not. They were both sporulating, so it was okay. But one of them was homotelic, so meaning that the spores that were produced change very quickly their sexual type, and it was very difficult, actually, to get hybrids from this and to have, let's say, stable spores and stable sexual type. So what we did actually was a mass hybridization to maximize the chance to get actually hybrids, real hybrids from both parents. For sure, segregants as well, haploid spores from both parents, but also self-diploid strains. And that are these strains that are actually coming exactly from the same parent. Maybe with a recombination, but from the same parent, so having more abilities to have the characteristics of the parent. And then from this, actually, hybridization, starting a long process of screenings and vinifications to be able to find right strains. And the first is the micro scale. And on the micro scale, what we will do? We will start to see what are the sexual type, if they are real hybrids or not. Then the H2S production with the bismuth reaction, with the hydrogen sulfide production, and then some microkinetics. And these hybrids score minus less than 2 for the production of H2S and less than 14 days of kinetics. We were able from 600 strains to reduce to, let's say, about 90 strains. And then we started, let's say, mini-scale vinification. And mini-scale means the scale is about the milliliter, 2 milliliters, on synthetic OIV medium, and we tried now, in that conditions, to see the main parameters. And what we saw is actually we reduced these 88 strains into 4 quite interesting hybrids, and you see that the parent one was really the one struggling with the fermentation, And all the other hybrids actually selected were among the fastest one with the parent, let's say the parent 2. But one of the hybrids was quite interesting for us. Why? Because it was fast, but also actually producing less acetic acid than the others and very low SO2. So we decided to investigate a little bit more about this one, and then to start upscaling and do a microvinification. Microvinification compared first to the parents. It was done with a partner that is called Twist Aroma, and with the microvinifications of the INRA Colmar on a muscat. And so we inoculated the strains in 25 liters Damjan, and then we adjusted the YAN on sugar, so the yeast available nitrogen on sugar at the factor of 0.8 with DAP. What were actually done the analysis was the partner, if you remember, was Twist Aroma, and Twist Aroma is coming from Twister. So we used actually a technique that is very interesting to reduce a little bit the limit of quantification of all the aromas. It's called the SBSE. Actually, it's the SBSE is actually the steer bar subtive extraction. So that's actually like a bar with a phase on it that will actually absorb all the aromatic compounds. These aromatic compounds will, can be done either inside the liquid or outside in the head space. And then there is a thermal deception unit from this steer bar, and we extract and concentrate the aromas, and you have a gas chromatography afterwards and a mass spectrum. So regarding the analytical parameters at the end of the alcoholic fermentation was really interesting, because actually it was what? The hybrid 3, compared to the both parents, was actually confirming the acetic acid production, very low. Very low as well, SO2 and acetaldehyde. If you see, there is no combined free SO2. But what we saw is actually there was no combined free SO2 as well. Why? Because it was favoring the malolactic fermentation. And this is actually all the parameters we had was this yeast showed a slower growth, so with a quite lower pitching rate and a higher lag phase, but was a fast fermenter. But what was interesting was this really low SO2 and acetaldehyde production. Moreover, we did this, let's say, aromatic analysis, and with the PCA, if you see all the other yeasts were here, and the parent 1 and parent 2 was there, the hybrid 3 was like an ovni there. And why? Because if you really see about the compounds, it's mainly all providing by acetate esters. And if you look at that, this hybrid was like 4 to 5 times overproducing isoamyl acetate compared to the parent, the parent 2 that was the one expressing the most these kind of compounds. So it was really like a very specific strain in terms of low SO2, but also overproduction of acetate esters. So we did microvinifications under dry form in that case, and then against commercial references. We did that with Institut Français de la Vigne et du Vin, so in France, and we adjusted the YAN function of the aromas we wanted to do. And what was really interesting was to see that the duration of the alcoholic fermentation and the total SO2 at the end of the fermentation was really, really low. In that case, was 0. But what was the most interesting was to see, compared to commercial reference in the market, if you do the OIV, so odor active value of 2-phenylethyl acetate and isoamyl acetate, it was really overproducing these kind of compounds, not producing any SO2 with a low H2S production, so no reductive flavors. This very high production, actually, of higher alcohol acetates was completely correlated with a train panel on the fruitiness side and on the aromatic intensity. So that was really interesting to see that. And then, as well, in the mouthfeel, it was really balanced with the reduced bitterness. So overall feeling about these products, about these compounds, was really like tasting like a candy. We did field trials in that case, so not controlled, but comparable trials in the field. In that case, it was interesting to test, in this case, on the same must, the test tank and the control tank, and we had a great, actually, help from HTS on that case in Italy. And we did 43 trials, different trials in the field this year. What was interesting to see, actually, we confirmed this lag phase, so this small problem of implantation of this yeast, but as far as it was implanted, it was really fast growing. And we confirmed a bit a moderate sensitivity to the sulfites, so correlated with the SO2 production as well of this product. But what was the most interesting for us, actually, was to see on the implanted trials the difference between the control yeast. And the difference between the control yeast was drastically higher aromatic intensity and fruitiness, and especially towards amylic notes. In the mouth, we also confirmed that actually the gustative balance and the reduced bitterness was there to really taste like sweet even without sugar remaining. But what was interesting as well is that it's for implanted trials, so where the yeast was 100% implanted at the end of the fermentation. But we also did several tasting on some of the non-implanted trials. And that's the percentage of implantation, 30%, 20%, 20%, 70% at the end of the fermentation. And what was interesting is actually every time we did this strain panel, there was a real trend or even significant trend towards this fruitiness and amylic intensity. So showing a good potential maybe for blends. So as a conclusion, first, hybridization techniques can overperform both parents' capabilities through adapted screening tests. These hybrid 3 distinctive notes were really the very low or even zero sulfite production, acetaldehyde production, up to 4 or 5 times more isoamyl acetate production than reference, with this minor problematic that is the medium lag phase. So targeted wines could be intense fruitiness towards really banana candies, floral notes, green notes removal with the action of the isoamyl acetate towards these kind of flavors, and the balance acidity, bitterness, sweetness. Nice choice for blend because of this very low production of SO2 and acetaldehyde and low SO2 wines. So actually we decided to first launch this hybrid 3 this year, commercially speaking, and it will be the SAF Eno HD A54, HD for hybrids, A for amylic notes, and 54, that is the number of the strain. And then I will let the floor to my colleague, Yorgos. Thank you for your attention.